All right, hey everyone. Okay, in this video, this is going to kick off our videos of the Earth's Interior and Plate Tectonics Study Guide help videos. Woo! All right, so I'm going to try to keep these videos as short and concise as possible, but I am going to try to also explain the concepts so that you're fully prepared for the test next week. So this is going to be broken up into 4 different videos. Watch whichever video you need to watch. Well, let's get started. The very first one, it's pretty simple. One of the questions on the study guide is asking about continental drift evidence. We did a whole note sheet on this. It's called Continental Drift Notes. Look in your Google Drive. You should be able to find it no problem. The 4 main pieces are the continental puzzle, matching rocks, matching fossils, and ancient climates. Now, if you use your continental drift notes, which would be really sweet, the whole point of the study guide is to help you review your notes. You're gonna see that you have them already filled out where you actually explain what they are. So the continental puzzle is when the continents look like they fit together and that over time they've drifted apart. They look like puzzle pieces that were once one. Another type is matching rock type fossils. That's just saying on different continents like South America and Antarctica, there's matching rock layers that are identical in composition and in the time period that they were created. And that is a pretty good indicator that at one point they were connected. Another piece is matching fossils, which is pretty similar to matching rocks, where we're talking about organisms that can be found on Australia, Antarctica, Africa, South America, but at a time when like plants, they couldn't move. We didn't have humans flying things around. So those matching fossils on different continents is a really good idea, a really good evidence that they were once together. And then finally, the last main piece is ancient climates. There is evidence that in Australia, Africa, and India, there were at one time glaciers there. And that's just not physically possible with where they're located today. So these are the 4 main pieces of evidence that Alfred Wegener used to support the idea that the continents once moved. So that's continental drift evidence. So we're going to pivot, but it's in the same note sheet where we talk about convection currents and density. So this is something we've been talking about a bit. Convection currents is just the idea that you have hot fluids that rise because they're less dense. So in this GIF here, we've got this really hot spot in our mantle. And because it's super hot, the particles get heated and they start to expand. And that's what makes them less dense. Remember that density is just saying how many particles we have in a given area. So if I have something with particles that are kind of spread out and then something with particles that are really tight together, this has a higher density in this region than that does. Remember, as things heat up, those particles get more energy. Remember the gases versus liquids and solids. So as things heat up, those particles spread out, and that's what decreases the density, causing hot things to rise. That's all convection is, hot things rising because they're less dense. And then as this stays up here, far away from that hot mantle, it gets cold. The particles lose energy and get close together again, and then it falls down. That's what convection currents are. Hot things rise, cool things fall. And that's all due to density. Plate tectonics is driven by this idea that there are convection currents in our mantle. So overall, plate tectonics is the idea that we have these large slabs of lithosphere. Remember that solid rock where it's the crust plus the top hard layer of the mantle? That's what the lithosphere is. And so plate tectonics is saying we've got chunks of lithosphere that are moving around on top of the asthenosphere. So we got lithosphere stacked on asthenosphere. And the asthenosphere has the plates constantly moving because of the convection currents in there. So as a really hot section rises to the top, it gets pushed sideways in the asthenosphere, which drags these plates with it. That's what plate tectonics is. That's all it is. We got lithosphere on top of asthenosphere. Convection currents in the asthenosphere causes that lithosphere to move. So it's because of the tectonic plates, in addition to this moving, when these plates spread apart, we get magma that gets to go all the way to the surface. That's constructive. We are renewing Earth's surface there. And in the subduction zone over here, whoop, it dives under. That's destructive, which is causing this old lithosphere to melt back into the mantle and recycle its way back through. In a different video, I'm going to cover subduction and constructive and destructive forces. So for this particular slide, you need to focus on plate tectonics is lithosphere on top of the asthenosphere. Cool, thank you. Subduction zones. Oh gosh, I forgot this was part of this video. So subduction zones, this is that convergent boundaries when one plate dives under the other. Remember, sub, like a submarine, it dives under. So when we have convergent boundaries, that just means we've got two plates, boom, slamming into each other. The denser plate will subduct, just like our convection currents, right? Hot things rise because they're less dense, cold things sink because they're more dense. It's that density that drives that whole system. So because the oceanic lithosphere is denser than continental, it dives under. So because it's more dense, it dives under this zone and it gets hotter and hotter. And the friction between these plates actually causes the magma, or this rock, to melt and turn into magma. And as it melts, it becomes what? Less dense. Yeah, because it's getting hotter. So as it melts, it becomes less dense, and it goes all the way to the top, boom, we get a volcano, which is constructive. It's making more land. But overall, here at this subduction zone, this whole oceanic plate is diving under, and this is destructive. It's destroying this old crust and recycling it and melting it back into the mantle, which is pretty sweet. So subduction zones, they just dive under, and that has to do with density. The denser plate will always dive under. The friction between those plates is ultimately what makes our volcanoes. Yeah, sweet.